Well, hello again everybody. Well, I was buying some stuff on Amazon the other day, and sometimes you get these little promotions come up on your screen prompting you to buy something else. And one of the things that came up was this plug-in cigarette lighter USB charger. And it's not the sort of thing I would normally be very interested in. But the Amazon listing did catch my eye because it claimed to have a 2.1 amp output at 5 volts. And of course, I'm guessing that's quite possible with a switch mode power supply. But yeah, again, I just wondered if it would actually sustain that, if it was actually capable of delivering what it claimed. So I thought I'd buy one of these and give it a try, because I think it was only like £2 or something. It certainly wasn't very expensive. So let's just have a look at it. And it looks pretty much like any other USB plug-in car charger. But as I said, the interesting thing about it is actually the output. Well, for a start, the input is kind of strange as well, 12 to 24 volts, and it's got an output of 2.1 amp. Now I'm guessing inside we're going to find some form of switch mode regulator, because there's no way that this thing could work at 24 volts, dropping something down to 5 volts at 2 amp. It'd just dissipate far too much power internally. But I'm still sceptical whether or not it is actually capable of outputting 2.1 amps. So I wanted to give it a try. Now it's branded as SDTEK, and the model number is UP-522B. It says it's got an input DC of 12 to 24 volts. It's got an output of DC 5 volts at up to 2.1 amps. It's Rolsch compliant. It's made in China, unsurprisingly. And the USB socket on the top is rated at 1 amp. And the USB socket on the bottom is rated at 2.1 amp. The question is, do we actually believe that? I actually don't know, but I would be very surprised if it does. So if we're in a gambling mood today, all start placing your bets now of whether or not this thing will be able to deliver 2.1 amps at 5 volts, because I'm very sceptical. But we will see.
Press bet now. Come on!
Now, to do our testing today on this USB charger, we're going to use a few different power supplies. I think the main one that we'll be using is this Charman Multicom power supply. It's got basically a cigarette lighter socket on the front of it, which can deliver up to 10 amps. And the thing about these power supplies is they're designed for use by ham radio operators. So in terms of switching noise and stuff like that, for a switch mode power supply, they are pretty good. So the front cigarette lighter socket that we're going to be using can deliver 10 amps, and the set of terminals on the back there can deliver up to 23 amps. And the back terminals, I've just got my Fluke voltmeter plugged into. So we're going to use the Fluke voltmeter here just for monitoring the output voltage. So I can see at the moment that we're getting a 13.86 volts out from the power supply. And the terminals, when you actually open these things up, the terminals at the back are actually pretty much connected straight through to the terminals at the front. So the 10 amp rating for the socket on the front is really just the rating for this particular cigarette lighter socket. Now these units also have a little fan on the back of them, which are firmly controlled, and to be honest, I very rarely hear this one ever come on, and I very much doubt it'll come on during our testing today. Now the rear sockets on the unit, which as I said earlier can produce up to 23 amps output, they've got a combination of 4mm banana plugs and also binding posts. And again, I would actually recommend these as being quite a good kind of lab power supply if you ever need to do work on like automotive car radios and stuff like that. You could probably, it's very handy to have a fixed 13.8 volt supply, because if you're plugging automotive equipment into your desktop power supply, you always run the risk of the voltage being set to the wrong level or something like that. Whereas at least you can't make that mistake with a fixed output voltage. So I do tend to use this when I'm working on automobile stroke RF transceivers and stuff like that. But yeah, I'm a big fan of this power supply. It's been very good. Now this is my mainstay power supply, which is another power supply made by TTI, which is Furley Fandar Instruments. I love that name, Furley Fandar, and this is the one that I use most of the time. Now this one is just a linear regulated power supply, and it doesn't have a fan in it or anything like that. And again, the model number for those playing at home is a PL330P, and it's rated at up to 32 volts at 3 amps, and it can do that quite easily without overheating or anything like that. So I've got the output from the power supply connected through to this little set of terminals here on my bench. So it just means that I don't have to have any test leads draping over everything. And I've got this connected through internally with some relatively thick wires, so you don't actually get really much of a volt drop up to about 3 amps, which is all the power supply is rated from. And I've also got another of these cigarette lighter plugs which I just keep permanently connected. But as I say, you've got to be very careful using these, because you don't really want to plug something into it and find you've got it set to 30 volts. That can really ruin your day. Now I keep this old iPad in the workshop just for looking at data sheets and stuff. It's convenient. So we'll just plug it in and see if it can charge that. So with the iPad plugged in and charging, the USB charge is outputting 4.97 volts at 1 amp. So that's pretty good, I think. Now I don't know if you'll remember, but a few months ago I designed this little USB powered DC load which you can actually connect to your laptop and carry automated test. But unfortunately it's only rated to 1 amp. Well, it would actually do more than 1 amp. I'd have to actually tweak some of the software inside this, because it's got some software limits set in here at 1 amp. And that was because I was just trying to control the power dissipation in the heatsink that I had it connected to. But yeah, unfortunately we're not going to use this today because it's only 1 amp and we need more than that. But what I'll do is, you might be interested in watching me construct this, so I'll put a link in the video so you can see that. So what we're going to use instead is our old friend, the Kirkisui electronic load, and we're going to be using this model number PLZ 300 watt electronic load. Now of course it isn't as advanced as many of the modern electronic loads that you can get on the market these days that have USB connectivity and data recording and stuff like that, but it's good enough for what I need. I mean, it's got the two main settings, which are constant current and constant voltage, but you can also put it into a constant resistant range as well, which I've never used, but you could if you wanted to. But the other feature that's good for testing, what would you call it? Not dynamic range, dynamic response perhaps of power supplies. It's got a feature here where you can actually make the load turn itself on and off, which, you know, simulates a varying load, and we'll maybe give that a try later. It's quite good for showing up inadequacies within power supply designs and feedback circuits and stuff like that, so we'll give that a try as well. It's fitted with quite a large cooling fan, which means it does sound a little bit like a jet engine starting up. But I've got to admit, I'm quite a big fan of this equipment. And unfortunately, the other minor niggle with it is that this voltage lamp here doesn't work very well. It seems to just float around all over the place, and I could do with repairing that at some point. But to be honest, I tend not to use the voltmeter on here anyway, because really you want to measure the output voltage from your power supply device. You don't necessarily want to measure it across the load, because then you're measuring the volt drop of your cables. So that's the reason I haven't bothered fixing this, because I don't really need this meter. I just use the meter here which has got the amps setting on it. That's the one we really need. Now in the past I've found it necessary to actually break out some of the USB connections, which is for this one the 5 volts, 0 and 5 volts, and also the data. So we're going to use this little breakout box that I've used here to actually get the connection to our USB charger. Now of course this isn't perhaps the best solution, because we're going to get bits of volt drops and stuff like that in this cabling, so it's not as exactly ideal. But you know, we're not doing laboratory class measurements here, we're just doing a quick and dirty test, so it's going to be good enough for what we're doing today. So what we can do with this is we just plug in the USB connection, and we're going to go again for the 2.1 amp. We'll plug this into here, and we can connect our electronic load using these banana plugs on the front here. Now because the voltmeter on our electronic load doesn't work very well, we're going to use this BK Precision 5491A 5000 count multimeter to actually monitor the output voltage coming from our USB charger. And what we'll do is we'll connect that up to the USB charger, kind of using what you might call a pseudo Kelvin connection. So we're taking the volt drop in this part of the cable in here just out of the circuit by going directly into here. But of course we're still going to get a volt drop in this part of the cable here, but yeah, we're not going to worry about that. Now for our first test, I think we'll look at the output regulation of our 5 volt USB charger as we increase the load current. Now at the moment the DC load is switched off, so you can see the open circuit voltage of the charger, and that's at 5.09 volts at the moment. So what I propose to do next is just to increase the load on the USB charger, and we'll do that in 500 milliamp steps up to the maximum output of 2.1 amps. And for every step we'll just record the voltage here. So we'll turn the load on. At the moment it's set to 0, so we'll just increase our current. So there's our first test point, 500 milliamps, 0.5 amps, and our output voltage is 5.05 volts. We're now at 1 amp and the output is 5.02 volts. 1.5 amps and our output is 5.01 volts. So now we're going to go all the way up to our maximum, which is 2.1 amps. And our output voltage at the maximum is a very respectable 4.99 volts. So it looks like I lost my bet there. This thing is capable of delivering 2 amps. Well, looks like I was wrong, and not for the first time. But I suppose it's not unexpected given that this is a switching regulator in this USB charger. But I'm still quite impressed with that. And let's just do a quick touch test. Yep, it's been running at 2.1 amps there for a few minutes, and stone cold. Very efficient. And with the aid of my beautiful assistant, I think we'll give this a 5-star rating. Very good. Now for our next test, I thought what we could do is we'll actually vary the input voltage to the charger and then see what, if any, effect it has on the 5 volt output. Now we're going to do this check for a couple of reasons. One is because it's quite likely that the output voltage from your car battery will vary slightly depending on whether you've got the engine running and the state of the charge of your battery. And this charger is also stated to have a DC input voltage of between 12 and 24 volts. And I thought we could put that to the test. Now we'll do that test again at the full rated current of the device, which is 2.1 amps. So we're going to use this power socket here, and this is connected to my lab power supply, which you saw earlier on the shelf. And just so you can see what the voltage is set to as we vary it, we're going to be displaying that here on the fluke meter. Now it's a bit of an old socket this, it's a bit grubby inside, so I'm just going to give it a bit of a clean first, because I did find it was making a bad connection earlier. And I think the problem with it is it's actually the centre connection, the positive connection right at the back here. So I'm just giving that a bit of a clean with some Electrolube type spray. Well, it's not Electrolube, it's deoxit, but it's all the same stuff. So at 9 volts, we're getting quite a respectable 4.9 volt output. Now, of course, it is interesting to note that this charger will work at such a low voltage, but it also concerns me a little bit that if you plug this into your car, now hopefully you've got a cigarette lighter socket that switches off when you turn the ignition off, but the fact that this will actually still draw power at between 5 and 9 volts, it'll start drawing power. It means that if you leave this charger plugged in, it could completely flatten your car battery. It perhaps would have been nice to see some kind of cut-off voltage in this, so maybe it stopped working for voltage below 12.5 volts or 12 volts, whatever it may be, but maybe just something that would just stop your car battery from totally discharging. But yeah, again, that's just me being a bit picky. So let's go to the device's rated input voltage now, which starts at 12 volts. And at 12 volts, we're at 4.9 volts again. 16 volts, 4.97. 20 volts, 4.97. And finally, the maximum rated input for this device, 24 volts. 24 volts, 4.97. And I'm going to give that another 5 stars. Now interestingly, our input voltage is 24 volts. Our input current is 530 milliamps, but our output current is 2.1 amps. So our little USB power supply seems to be performing a little bit of magic there, doesn't it? It's only actually taking 0.5 amps in, but on the output it's supplying 2.1 amps. And this is really the wonder of switch mode power supplies. And what we would have to do is we actually have to do a little bit of a back of the fag packet calculation, because what we need to be considering is the actual power on each side. So we're supplying 24 volts in, and we're supplying 500 milliamps in. So our power is 24 multiplied by 0.5, which equals, even I can do that in my head, 12 watts. Our output voltage is 4.938 and our output current is 2.1 amps. So what's our power? I'm going to use a calculator this time. 10.36 watts. 10.36 watts. Now I'm sure most people out there won't be surprised by any of this, but I have to admit I'm still quite surprised, because I'm still somewhat in wonder of these little switching power supplies. Because back in the day, you wouldn't have had these little switch mode power supplies. If you wanted to get a 5 volt output from 12 volts, you would use a linear regulator. And the thing about the linear regulators is they're very inefficient. And just to kind of give you a demonstration of that, we'll just do a very quick and dirty calculation. So this is a 7805 something or other, which yeah, probably was only rated at 1 amp anyway, but there is higher current versions available. So let's just have a look at how we would have done this back in the day. So if we just follow the example we had previously, we had 24 volts going into our 5 volt USB charger, and we had 5 volts coming out. We had 2.1 amps. So basically the current to the input to our regulator is also common to the output current. So if you have 2.1 amps going in, we're effectively going to have 2.1 amps going out. So if we have a look at some of the powers involved here, 24 volts at 2.1 amps. 2.1 amps times 24 volts. So the input here would be 50 watts, 50.4 watts. But our output power, our useful power, would be 2.1 amps times 5. 10.5 watts. So basically, for 50 watts we would be putting into a linear regulator, we're only actually getting 10.5 watts of useful power out of it. So again, if we just do the maths there, 50.4 minus 10.5 is 39.9 watts. So to get this into perspective, our 5 volt regulator here would be trying to lose 39.9 watts of power. Now it wouldn't manage that, well, it might manage it for like 1/100th of a second before it just destroyed itself, but you couldn't get that amount of heat energy out of the die, so you wouldn't be able to actually construct this device using linear voltage regulator technology. And that's what I still think is amazing. These things are just so efficient. So if we look at our switching regulator first, we was getting 10.36 watts of useful power out of it. and we were putting in 12 watts from our power supply. So if we just do the math on that, 10.36 divided by 12, and then we'll multiply that by 100. So that gives us an 86% efficiency. So if we consider the same thing now for our linear regulator solution, I'm going to say, let's say the useful energy out would have been the same. So we'll call that 10.36 watts again. And we're going to divide that by the energy we were putting into our regulator, which we said was 50.4. Now I assume I've done that right. I've never actually bothered to work out efficiency before. Again, not something I often need to do. But I just think that's staggering. That's interesting. Hail the switch mode! Hail the switch mode! We're not worthy! We're not worthy! Alright, until next time, thanks very much. Bye for now. Banzai!